Model laws in model analysis. Introduction to model laws. So the model laws are essential principles that guide the scaling of a fluid mechanics. So they allow for the prediction of full scale behavior based on the experiment conducted on a smaller model. So understanding the model laws is very important for an engineers to ensure the accurate results in fluid dynamic studies. Importance of dimensional analysis. So the dimensional analysis helps in deriving the model laws by comparing the dimensions of physical quantities. So it simplifies the complex fluid mechanics problems by reducing the number of variables involved. So there are two methods of dimensional analysis. One is the Rayleigh's method and the another one is Buckingham's pi theorem. So the Buckingham's pi theorem is a fundamental tool in dimensional analysis, providing a systematic approach to derive the dimensionless groups. Buckingham's pi theorem. So Buckingham's pi theorem states that if the physical problem involves n variables and m fundamental dimension, the variables can be arranged into n minus m dimensionless groups. So these dimensionless groups serves as an basic for developing the model laws applicable to the fluid dynamics. So the theorem facilitates the indications of a key parameters that influences the fluid behavior, aiding in experimental designs and analysis. Reynolds number and its significance. So the Reynolds number is a dimensionless quantity. So there are various dimensionless quantities like Reynolds number, Faraday number, Mach number, Weber number. So each dimensional quantities helps in predicting the flow regime characteristics in fluid mechanics. So the Reynolds number, so in this number, viscous force is in predominant flows. So it is defined as the ratio of inertia force to the viscous force and is critical in determining whether the flow is laminar or turbulent. So the laminar flow is said to be of a smooth flow if the Reynolds number value is less than 2000. If the Reynolds number value is greater than 2000, the flow is said to be a turbulent flow. The model laws often dictate that the Reynolds number must be matched between the model and the prototype. So the model is an prototype is an actual system, and the model is a replica of a prototype for accurate results. Faraday number. So the Faraday number is another dimensionless parameter. So it is a ratio of inertia force to the gravitational force. So in this, the gravity force is predominant. So based on the Faraday's number, we can determine whether the flow is in a critical flow, subcritical flow, or supercritical flow. So what is a critical flow? So if the critical flow is, if the supercritical flow, if critical flow is, if the value of the Faraday number is equal to 1, the flow is said to be critical. If the value is greater than 1, the flow is said to be supercritical. If the value is less than 1, the flow is said to be subcritical. So it is particularly relevant in free surface flows such as rivers and overwears. So in model testing, maintaining the same Faraday number between the model and prototype is essential for accurate predictions of wave patterns and flow behaviors. Mach number in compressible flows. So Mach number is a critical dimensionless quantities in compressible fluid flow, representing the ratio of flow velocity to the speed of the sound. So it's very important for analyzing the flows in high speed applications such as aerodynamics and gas dynamics. The model testing must ensure that the Mach number is appropriately matched to achieve the reliable results in compressible flow scenarios. Similarity criteria for fluid models. So the similarity criteria define the condition under which the model accurately represents the prototype. So these criteria includes geometric similarity, kinematic similarities, and dynamic similarity, each addressing the different aspects of a fluid behavior. The proper adherence to the similarity criteria is vital to ensure that the experimental results can be scaled to real-world applications. Scale effects and the limitations. So the scale effects refers to the discrepancy that arises when the scaling models, which leads to inaccurate predictions if not properly managed. So limitations in model laws can be caused by factors such as turbulence, surface tensions, and non-Newtonian fluid behavior. So engineers must carefully consider these limitations when designing the models to ensure the valid and the reliable outcomes. So the practical applications of model laws. So the model laws includes Reynolds model laws, Weber model law, Faraday model law, Mach model laws. So these model laws are widely used in various fields including the civil engineering. So they facilitate the designing and testing the structures like bridges, aircrafts, pipelines under a fluid flow conditions. So successful applications of model laws can lead to cost savings and improved safety in engineering projects.